Okay, welcome to our channel. If you are new, please subscribe, like, comment, and share. Thank you so much. Today, we are talking about the equilibrium of forces. This equilibrium of forces is a topic that you can find in both physics and further mathematics. And here, I will do it in the sense that it will comprise of physics and further mathematics. Now, first thing we have to learn is that what is the meaning of equilibrium? Equilibrium. When we say equilibrium in physics, equilibrium is a state of an object with respect to a given observable quantity. Now, if you look at this, this is a ruler. This is a ruler. If this ruler, this is a state of this ruler. So for this ruler to be balanced, let's say I put one weight here, I put another weight here. So if you look at this diagram, it says equilibrium is a state of an object. This state of a ruler with respect to a given observable quantity. So these are the given observable quantities. That means for this ruler to be balanced, there are some forces, there are some observable quantities, there are some quantities that make it to be at this point, at these positions, at this state, with respect to a given observable quantity. During the time for which there is no change in that quantity. Can you see now? These two observable quantities make this ruler to be balanced, and there is no change in that ruler. That means if I should change the position of this observable quantity that is here, the mass that is here, that means this ruler will not balance again. It will change the state of that ruler. That's why we said, so for me to say this ruler is at equilibrium, so there won't be any change. There won't be change in the quantity. So there won't be change in this quantity, and the state of this ruler will not change. So that means the ruler is at equilibrium. Is at equilibrium. As an equilibrium is a state of an object with respect to a given observable quantity during the time for which there is no change in that quantity. Now, we have types of equilibrium. Types. We have the kinetic or dynamic, and we have limiting. We have kinetic or dynamic, we have limiting. Though we have thermal equilibrium, but this is another thing, that's thermodynamics. But majorly we are going to be limited to this kinetic or dynamic limiting equilibrium. Now, after that, what is the conditions for a body to be in equilibrium? A body is said to be in equilibrium when, number one, when the body remains at rest or moves straight line with constant number two, when the body is either rotating or it's rotating at a constant Now, what are the conditions for a body to be in equilibrium? These are the two conditions for a body to be in equilibrium. So they said the first condition for a body to be in equilibrium is that the body as a whole remains at rest. Remains at rest or moves in a straight line with constant speed. If the body remains at rest, that's a limiting equilibrium. That the body is not moving at all. When the body remains at rest or moves in a straight line with constant speed, that means even if the body wants to move and you say that body is at equilibrium, that means that body is moving with a constant speed. If it is moving 2, that will be 2, 4, 6. And with a constant speed, that shows that that body is in what? Is in equilibrium. Now, number 2 says that the body is either rotating at all, or is rotating at a constant angular velocity. Even if the body is rotating, the body must be rotating at a constant angular velocity. The angles at which the body is rotating must be constant, so that such a body is in equilibrium. So these are the conditions for a body to be in equilibrium. The body remains at rest or moves in a straight line with constant speed. The body is either rotating at all or is rotating at a constant angular velocity. And it's either if the body is not rotating, at all, and the body remains at rest. So that is the under limiting frictions. The body is not rotating at all, or the body remains at rest. Those are the limiting frictions, limiting equilibrium. But if the body is moving in a straight line with constant speed, or is rotating at a constant angular velocity, is moving with a constant speed in a straight line, or is rotating at a constant angular velocity, those are the dynamic equilibrium. Okay? Those are the conditions for the body to be in equilibrium. So, what are the things to learn after that? We're going to talk about the resultant and equilibriums. When I said resultant and equilibrium, what is a resultant? You know, in vector, we have learned resultant, scalar and vector. And when we are calculating vector, we are taught resultants. So in our coming videos under the vectors, I'm going to expatiate the resultant very well. But let me quickly say something here. Resultant is a single vector that have the same effect on both magnitude and what directions, as the two vectors are taken together. So what does that mean when I say that? Okay, let me write this. The resultant force is that single force which acting alone will have the same effect in magnitude and direction. As two or more forces acting together. As two or more forces acting. So this is the definition for the resultant. The resultant force is that single force. Is that single force which acting alone will have the same effect in magnitude and directions as two or more forces acting together. I'm going to give you the diagram illustration. I'm going to show you what I mean. Like, let's say these are two forces. These forces go to north. Is it north? Is it east? This force goes to east. If they ask you to find the resultant will be in the middle. This will be the resultant force. That's why we said resultant is that single force which acting alone will have the same effect in magnitude and direction. These two forces will represent my magnitude and directions. Magnitude and direction. You know, if I write something like this effector, so this indicates magnitude and directions. So these two forces, they indicate magnitude and directions. That's why I said the resultant force is that single force which acting alone will have the same effect in magnitude and direction as the two or more forces acting together. These are the two or more forces that are acting together, and this resultant will have the same effect on both of them, because the formula for resultant is for these that are forming angle 90 degrees. Like the Pythagoras theorem. This is a formula for the resultant. For the two forces that are forming angle 90 degrees. If it is less than 90 degrees, we're going to explain that one in factor later. You know, these are an acute angle less than 90 degrees. The resultant also will come from the middle, having the same effect as the two forces are acting together. So these two forces represent the magnitude and direction, and this will be our resultant. And here resultant here will be minus 2ab. Let's say the C that I'm looking for. Minus 2ab cos C. We use cosine rule formula. If it is less than 90 degrees or greater than 90 degrees, we use parallelogram for resultant. That is for resultant. So in the vector field, we are going to use with all this one. And resultant can be, you know, all these ones are two forces. According to that definition, they say the resultant force is that single force which acting alone will have the same effect in magnitude and direction as two or more forces act together. It can be two or more forces. All these ones are two forces. Even if you have something like this in physics, let's say you have plenty forces. This is your force, and we have angle here. We have angle. We have an angle. Even in a situation whereby we have many forces like this, we are going to resolve everything to what? To x and y. We are going to resolve it to x and y, and the resultant will now come to place. We are going to treat all these things very well in vector. This, we are going to treat it very well in vector. We are going to resolve everything to x and y, because they say as two or more forces acting together. In fact, we can have something like this. Something like this. So we are going to resolve everything also to x and y, and the resultant will take place. We can have something like this. This can be vectors. So we are going to resolve it also to x. So resultant is that single force. Acting alone, we have the same effect in magnitude and direction, and the two or more forces are acting together. Now, what is now equilibriums? The resultant and equilibrium. Now, when we say equilibrium, this is a definition for equilibrium. It says the equilibrium of two or more forces is that single force which will balance all other forces taken together, and it is equal in magnitude but opposite in direction to the resultant force. That means equilibrium balance is the work of equilibrium is to counterbalance all other forces that are coming together. And equilibrium is always the same or having the same magnitude with the resultant but in opposite directions. What does that mean? If I have two forces like this, this is the force, the first one is second. Now the resultant will come here. This is my resultant. So the work of equilibrium can be here. This will be equilibrium. So equilibrium and resultant, they are the same thing. If I've worked it and I got my resultant to be 10 Newton, so equilibrium also is 10 Newton. So having the same magnitude with resultant force, but in opposite directions. That means if I should get resultant to be like 10 Newton east, so equilibrium will be west. If I should get resultant to be 10 Newton north, equilibrium will be 10 Newton south. So it's always in the same magnitude resultant, but in opposite directions. That's why I said the equilibrium of the two or more forces is that single force which will balance. Can you see the work of equilibrium? It balances the two forces, which will balance all other forces taken together. It is equal in magnitude but opposite in direction to the resultant force. Now you can also assume this one to be equilibrium, but you call this one force. It will balance the two. Anyone you take, if you call this one equilibrium, it will balance the two. If I call this one equilibrium, it will balance this two. But mind you, it's always opposite to your resultant, but the same magnitude. Okay? Before we explain triangular forces, let's solve one question under this.